I like to know my audience. Who here is not CS? Do we have double E's? Do we have MBA folks? Double E, please, I really want. Okay, great. So like a handful of double E's. Okay, right. So we won't talk only about the software. We'll talk about the hardware as well. We're gonna cover everything anyway, but I won't skip the hardware part. Let's see. Any business
This is no
folks?
trash.
Even if your background is double E or CS. Okay, okay, great. My business cards are here. You can grab them afterwards. I have some props. Yeah, we'll get to them. I have a lot more material than we can cover in an hour. Just I'm always ready for any questions. I can jump around. Do you all know what Quanergy does? We do. I mean, it's really hard to not know what Quanergy does these days. We're almost in the news every day. We've been getting almost every award. Top 10 startup, top 10 this, and top 2 this, and which is great. But that comes with lots of hard work and resulting business activity, which is also great. But that comes with very little sleep, which is okay. So we make LiDAR. We are famous for our core technology, which is the solid-state LiDAR. Having said that, the software behind the solid-state LiDAR is where the brains are. And ultimately, we have multiple layers of application and perception, smart perception software, and then scenario analysis, decision making, and so on. All of these layers are laid on top of the basic point cloud that you get out of a 3D LiDAR sensor. We'll talk about all this, and then there's the data you collect, the big shovel that we use to fill the dump truck that the cloud is, and get things processed and fused between different sensors, not just for LiDAR. We'll talk about fusion between LiDAR and video and radar and so on. The company is 3.5 years old, but in terms of introduction, I worked on the core chip that is the core of the solid-state LiDAR 25 years ago. For my PhD, it was sponsored by DARPA. It was the biggest chunk of my PhD at Columbia. Then I went on to get business degrees from, in this order, Harvard, MIT, and Stanford. This is my fourth startup. All my startups are based on, the hardware part of them is always silicon photonics. I've built and sold 3 companies. 2 are telecom companies. 1 is a solar company, and now this is laser sensing. But that's really, that's exactly what I worked on for my PhD. And so to avoid too much suspense and people wondering what the product looks like, let's just show it to you right now. That's the solid-state LiDAR. You compare it with what we commonly call the KFC bucket on the Google car. This is a smaller, lighter, lower power consumption, completely solid-state. Macro level, micro level. So this does not have micro MEMS mirrors that the naked eye does not see. No, nothing moves. Truly solid-state based on optical phased array, beam interference. It's an optical version of the phased array radar. And now this, you never see it on a vehicle. So it's not only small, it's also hidden. It's always behind, inside the side view mirrors, in the bumper, behind the grille. And so a car that has this basically looks like it has nothing. And that's the point. That's the kind of car you want to buy. You're not going to buy a car that looks like it has a lab bench on top. It's cool for pilots and yeah. But when you buy a luxury vehicle, you don't want it to have a bunch of instruments on top. So our mission basically is just to do 5 things. That's all we do. We save lives, energy, space, time, and money. And so saving lives is safety, and then the other four are efficiency. So we are energy efficient, space efficient, time efficient, and cost efficient, our solutions. My background in the industry, I'm going to just flash this. I'm not going to spend too much time on this. Just so you see the companies I worked with and sold, and then I stay with the parent company for many years, actually, typically, which is not common for entrepreneurs. Um, and then we did some acquisitions over time. Long story short, I started after my PhD at Allied Signal in Morristown, New Jersey. We became Honeywell after we acquired Honeywell. Started three companies, sold them, sold one company to Corning, one to DuPont, one to SK Energy in Korea. Became the CTO of Sun Edison, and then now Quanergy. What we are about disruption through innovation and through business model innovation, technical and business model innovation. We disrupt the transportation space as well as security, industrial automation, mapping, digital navigation, as well as location-based services. In mapping, we are mapping the world, making a unit like this, the solid-state LiDAR, for a couple, making it available for a couple $100, meaning our cost, you can guess, is about half of that. Allows it to go in every vehicle now. It's no longer the $80,000 unit that you see on a typical Google car. We love Google, by the way. Not trying to say anything bad about Google. It's just, I mean, they use it to develop software, right? So whatever works to develop software, that's fine. So, but in that case, when it's a mechanical LiDAR and you're using it for development to develop software, if it breaks, okay, you go back to the shop, you replace it. But when you're using it to actually enable an autonomous vehicle and you're taking a nap, it's not as cool when it breaks. It has to be solid state. And that's not just our opinion because we have this. We have this because that's what the customer said. Um, location-based services. Ultimately, you can imagine a smart IoT, Internet of Things, where each thing doesn't just tell you where it is, it shows you everything that's going on around it. And that's a very smart IoT. So business model, basically, yes, we do have core hardware technology. We have a lot more software than hardware, multiple layers that I described, and ultimately we will get into data services. And that's our ecosystem. We have the core hardware, the data processing on board that controls the systems that control the vehicle, and we build maps using that data. We have we communicate in real time using a cellular connection, observations. An observation can be any object around you, a pedestrian vehicle, debris, pothole, etc. It can be a traffic condition, a weather condition, accident, so on. All of that gets communicated immediately via a cellular connection. On average, a car driving in moderate traffic, it collects about 25 observations per minute. Each one takes only 1 kilobyte to communicate. Type, location. Driving a couple of hours a day, 5 days a week, that's really just 50 megabytes per month. So it's not that bandwidth hungry. So any very basic data plan can handle that. Then you need the Wi-Fi connection to upload to the cloud the base map. You're collecting observations, communicating those in real time to everybody else who has a system like yours, so they're aware of what's going on. Then the base map where we are building in the cloud a global, centimeter accurate, daily updated, colored point cloud map. That is certainly a lot more data intensive. If you drive 8 hours a day, 5 days a week, in 1 week you'll collect about a terabyte of data. So you definitely need for a couple hundred gigs per day. You need a Wi-Fi connection. every vehicle has a Wi-Fi connection at some point. Even so, for a personal vehicle, that's easy, right? I mean, you're gonna park your car in a garage at some point. Even a UPS truck that's driving most of the time, at some point, is gonna go to a loading dock to get loaded, and it's gonna be waiting there for a couple of hours. That's enough to upload all the data it collected, and it downloads, refreshes deltas based on what everybody else has collected for the area of interest. So in our case, say the Bay Area. So an IoT roadmap would look something like this. It started in the early day in RFID used to be considered something you stick on something, and now okay, everything is tagged and you have an IoT. These days it's much smarter. It's you have um, uh, you have sensors that detect, classify, track objects. You have the ability to crunch onboard that data to make decisions using data fusion between different sensor types, LiDAR, camera, and radar. Uh, so, and if you're doing that in the context of deep learning, now you need an advanced processor. You need a GPU. We are working very closely with NVIDIA. We also work with Freescale and others um, on on the all the CUDA development. So a new paradigm in 3D sensing involves basically disruptive hardware technologies, 3D sensing LiDAR that are solid state, embedded processors based on GPU like NVIDIA's, and a good performance but low cost IMU. And those are available these days based on MEMS. Then you have so you have those core technologies. You have advanced systems that use these technologies, and those can be autonomous driving system (ADAS), or they support smart homes, smart cities, 3D aware devices. We'll talk about all this, and ultimately, smart solutions include that the global map I talked about, which is centimeter accurate in 3D, in color, and so on, updated daily. GPS-free navigation. When you have a map when you have a high definition map that's really high quality, high accuracy, now you can navigate offline. You can navigate offline. You don't need a GPS to navigate. The whole issue of urban canyons, what happens when you're in a tunnel and so on, goes away when you have on board all the information you need to navigate, and you're sensing constantly and locating yourself. And smart IoT is just such a broad space, and ultimately will change lives as we know them. Um, the we address many markets. Let me jump ahead, show you the big boring bullet list. It's going to make you dizzy. About 3 dozen different applications. We bucket them into 4 pillars: transportation, very broadly defined; industrial automation; mapping, terrestrial and aerial; and security. Security is defined as everything from smart home to smart cities to smart borders. And here are some examples of applications, and I point your attention to the fact that, for instance, in vehicles, that's almost obvious at this point because we talked so much about this. It's such a hot space. You probably have a good idea how that's used. But as you can imagine, also every drone company wants to work with us. You have the lightest weight, lowest power draw, uh, highest resolution, lowest cost sensor, smallest size. So that's a no-brainer for drones. Um, and ultimately, we're going to be able to fit in a handheld device, in clothing, so on, when the whole device is on a single chip, which pre-packaging has about this size. When you package it, it's a few millimeters thick, and now you have high-end, um, high performance type of LiDAR. This is not like the gaming LiDAR you can buy these days that has only a 10-foot range, that works only indoors when there's no sunlight, and that has low accuracy. If you walk around the house and you come back to where you started, it looks like you're off by 10 feet and so on. That's not what this works outdoors, has a 300-meter range, works in bright sunlight, has high resolution. This is the kind of thing that if you had this on a cell phone or on any device, you can go like this and map big architectural structure. You can map whatever you want, capture a scene, or just by waving this around. So that's the future. Everything we do is by design based on silicon CMOS. So all the individual components that go into making this particular multi-chip module-based solid-state LiDAR, when it becomes a single ASIC, can be integrated on a single substrate because it's all based on standard silicon CMOS, and that's why it's also a very low cost. You see the business part of this device. You see this chip right here, which is about 4 by 4 millimeters. You can calculate how many you can get out of a 12-inch wafer, and the yields have been phenomenal. We have not had a chip that does not work because we have developed calibration hardware boards and calibration algorithms that calibrate out imperfections in fab. So far, after we do that, we run the calibration. So far, every chip has worked. So that gives you an idea how we can hit the kind of numbers we've been talking about. We sell this a couple $100 in volume, and this is going to be below 100, potentially below $50 in volume. But I told you about what it does, the grade, the range, the environmental conditions that it can deal with, and so on. So I don't want to hear I can buy a gaming LiDAR for $10. This is just totally different. So the products we build based on these technologies and these capabilities, they lead in cost, performance, reliability, size, weight, power consumption. Let me clarify. By performance, I mean specifically range, how long it is, accuracy, as well as resolution. So accuracy we define as depth accuracy. Resolution is lateral resolution. Reliability, we both mean lifetime, how long it takes before. Mean time between failure is very high. Mean time between failure for this is over 100,000 hours of operation. Mechanical LiDARs typically have mean time between failure below 1,000 hours of operation. Some of them have 100 hours of operation. As well as, so lifetime is one thing, and the other thing is the ability to do signal processing and drop out false signals, identify false signals from false positives and false negatives from real signals. In rain, snow, dust, anytime our laser pulses hit an aerosol, any kind of solid in the air, they get broadened. And when we see that signature, we know it's not a real return. But when they hit a real object, pedestrian, vehicles, etc., we don't see that effect. I'll show you some examples that were actually an example that was run live at the NVIDIA booth at CES, where they had it rain and they had video on LiDAR and our LiDAR, and you'll see the difference. So that was the application part. Before we get into the more technical part, any questions about what the product is and the technologies behind it? We'll talk later about how the technologies work, and the appetite of different markets. So this is the part where we want to discuss more markets and applications and address any questions you might have.
Interesting. How many do you have in the car?
Minimum configuration has 2, front right, front left. That's all you need. And we are going to embed video in this LiDAR, so just for color, not for perception. Some people use video for perception. I just want to be able to see the traffic light. I want to be able to read signs. and I want to colorize the point cloud to just create a data set that's just more valuable. 2 units. This shows the advantages of LiDAR versus radar versus video. No one disagrees that LiDAR is the most capable perception sensor. Some people argue that it's an overkill when it was very expensive before we came along. People were arguing that it's an overkill. It's too capable. You don't need something that's that capable. You can do okay with a whole bunch of with a suite of sensors, including ultrasonic sensors, video cameras, and radar. A total of 24 sensors, 12 ultrasonic sensors, 6 radar, 8 video cameras, and you can get the job done under most conditions on a highway in good weather. But now with the introduction of this LiDAR to the market, you won't hear anyone say that LiDAR is not needed. Before they were justifying why they're not using it. It's the cost. Yeah.
By the way, why is radar better than LiDAR in some cases?
Yeah. The main case is fog. In very thick fog, that's the weakest. That's the weakest link for
What wavelength the radar or the LiDAR laser you're using?
right. We're using 905 nanometers, so we can stay in silicon CMOS. That's why. That's why exactly. I want to be able to detect in silicon. Silicon stops detecting at 1100 nanometer. I want to be below that, and I want to use lasers that are already produced for different markets at very low cost. I want to buy my laser chip for a couple of bucks. You could go to 1550. Now you have to detect in 3.5 compound semiconductors, in gas-based detectors, and you have, then, and you can use a higher power laser. But so the laser becomes expensive, the detector is expensive, everything becomes more expensive. So
what's your beam width?
well, there's some divergence. So and we actually have the capability. I'll describe 7 unique capabilities we have, because this is solid state and it does not have a physical configuration that determines the collimation. It's all software controlled. What I can give you is the minimum spot size. You can make it as big as you want. The minimum spot size at 100 meters is 3.5 centimeters. Typical mechanical LiDAR, such as the one on the Google car, at 100 meters, it has a spot size of 2 meters. And now we have 1.5 inch with this. But you can make it as big as you want if you want. We'll talk about all this unique capability. So we always recommend having 2 LiDARs, front right, front left, and 2 radar, looking forward and looking back. And that's a complete system in terms of the sensing suite.
What frequency radar are you using with your LiDAR?
66 gigahertz.
Okay.
Yeah. Our partner is our closest radar partner and tier 1 partner in general is Delphi, and so we use their radar. So this shows now physically an installation. The Google car that we all know and love, with the scaffolding on top that holds the bulky, heavy unit, so on, which is fine for R&D. And this vehicle was a gift to us from our partner Mercedes-Benz, and we demonstrated that live at CES 2 months ago in January. This black fascia was actually designed for us by Delphi. It's IR transparent. It's basically the same material that we make this cover out of. IR has more than 95% transmission through this. So you don't see the LiDAR, and that's the beauty. You just see some shiny black fascia. It looks beautiful, and it's something that people would buy. It looks stunning, and you don't see any contraption on the outside. And basically, for a total of $1,000, you can have a full autonomous vehicle system. You can make a vehicle autonomous with a system that has 2 LiDARs, 2 radar, accessories, software, plus margin, 1,000. People used to think that it would take. If you look at some reports written by the robotics office of the U.S. Army and so on, 3 years ago, they used to say it takes about $200,000 to make a truck autonomous. Now we're down to 1,000. This is our roadmap. So I have to say the first LiDAR we made is also mechanical because it's easy. We were able to get to market quickly, and we still had the smallest size, lightest weight, lowest cost, highest performance, highest reliability, and lowest power consumption compared to any other mechanical LiDAR. But still, it was mechanical. It was not solid state. Solid state has all these advantages to a greater extent, and it is completely solid state. Ultimately, everything will be on one chip. You embed that in a cell phone, in your clothing, in your hat. I mean, when you think of the applications, I mean, this can make blind people see. You can send a chirp or audio or some kind of even a brain signal that allows a blind person to see. The applications are almost limitless.
So is your chirp about a 100 picosecond range or something like that?
About that, yeah.
Yeah.
Right. You must have looked into that, yeah.
No, I used to work in radar.
Oh, okay. You see the pricing here. Well, say it again.
Default numbers.
Yeah. And as I point out here, the video cameras will be integrated in this just for color. Everything we're doing now and we'll do in the future will be all solid state. Our first vehicle, which was also a gift from Mercedes-Benz, we mounted our mechanical LiDARs on it. They're smaller; they're about this big, the size of a small coffee mug. But still, it was sitting on the outside on the baggage rack and so on. It's not as easy to integrate that into the body of the vehicle. But that's just the Gen 1, which is not for automotive applications. That's still fine for security applications, static applications. The problem with the vehicle, you hit potholes, there's vibration. It's not an environment for a mechanical solution. If it's a static installation, a security installation, and a static installation, mechanical LiDAR might be okay. It gives you a 360 view. This one, as you can imagine, well, theoretically, the most you can get out of the face of a chip is 180 degrees, right? You're not going to start to send light out the back of the chip, right? So we actually use the central 120 degrees to get the sweet spot of scanning. If you go too far to the edge, the range gets the amplitude of the signal decreases and the range decreases. So this is 120 degrees. A mechanical 360. If it's sitting on a pole and doing monitoring for road intersection, railroad intersection, monitoring some kind of safe site, industrial facility, an oil and gas field, whatever it might be, a border. I mean, this is, I mean, instead of building a big concrete wall, Trump should consider you. Exactly, I know. I can see your faces. Don't get me started either. But all kidding aside, you could have one of these every 500 meters or so, and it's smart because it's gonna see as soon as someone starts to approach, and you dispatch security can be sitting in an air-conditioned office, and you dispatch someone when there's a known event, as opposed to patrolling the U.S.-Mexico border or whichever border, right? It tracks, it detects, tracks, and it's very persistent. Meaning, our software is so smart that once it knows that there was something here and if someone hides behind the bush, it's gonna remember that sucker just hid behind the bush, and I'm gonna wait till he appears again. It's not that you cannot. It's very very persistent. Um, we have 8 patents filed. They should start issuing soon. The company is 3.5 years old. We start to file patents about 1 year into the company, and over the next year they should start to issue. We have about 15 more in preparation. You've seen this, you see the real thing here, so you don't need to spend time on this. It's 9 by 6 by 6 centimeters. So the principle of operation, it's an optical phased array. An optical phased array. You can take pictures if you want. We're going to give you the slides as well. Yeah. Basically the business part is this chip here. So it's a chip of about this. I don't know if you can see from afar, but the chip, the business part is this piece of silicon that's about 4 by 4 millimeters.
How many arrays do you have there?
See, this is one array that scans in the 2D space. This has a 120 by 120 degree field of view. This is, of course, a cartoon. The actual circuit is a lot more complex. When you add the different, there's the photonic circuit. There's the interconnect layer to bring the control signals. There's the actuation elements and the out-of-plane coupling that sends the light from being guided inside the chip to come and out to come basically normally to the chip. And now those beams, by controlling their phases, we can get them to create a spot size of any size pointed in any direction within the entire field of view. That gets calibrated once in the factory, and it's good for the lifetime. Some unique capabilities that no other LiDAR has, only because this is solid state. You can adjust the window of interest within the field of view. So if the unit gives you 120 by 120 degrees, you might say, I'm interested for this application in 120 by maybe 10 degrees. If it's a vehicle looking mostly at the horizon and so on. If it's a big mining vehicle that's a 3-story tall and it's looking at people walking down, and it's trying to not flick the dump truck that's trying to fill and so on, they would probably use the full 120 by 120. It depends on the application. And smart home applications, you also want to see everything that's going on around you. For security applications.
That's actually a question I had for you in terms
Okay.
of mining.
Yeah.
If you're using
Yeah.
the controller, so is like Rio Tinto Mining Company the firm you guys are using with your earth movers and stuff like that with your LiDAR?
I'm sorry, what was the question?
I was just wondering if the Rio Tinto Mining Company was the company that was using your LiDARs on their earth movers.
No. Let me think if any mining company. I'll show you some customers whose names are public. I'm not gonna disclose any customer names where we don't have their approval none of the mining companies gave us the okay to disclose their name. I can tell you our top 2 mining companies, one is American, one is Japanese. Distribution of points. When you collect a point cloud in a mechanical system, everything is set. So it has multiple layers that are spinning or scanning or oscillating. Distance between them is set. The resolution of data collection is set. Here you can change the point distribution based on the application. You can say I want a higher point density along the horizon, where I'm looking at what's going on the road, trying to detect every little thing, a baby, a small animal, a pothole, and so on, a soda can, debris that fell off a truck or something. But when I'm looking up and down, I just want to see the lane markings. When I'm looking up, I mainly want to see bridges, signs, or if there's a road in front of you that has an upslope, you want to actually detect the vehicles on it before you climb up that slope. Um, Random access, you can do completely random access with the system. It takes the same amount of time to go from any direction and with any spot size to any other direction with any other spot size. Uh, so that has advantages based on the scene you're looking at. Also in terms of signal to noise ratio, because when on the receiver side, if the spot you just hit, you did not just hit before that the adjacent spot, you don't have electron leakage, and that helps you with signal to noise ratio. So you can jump around, have an algorithm that has optimal configuration for the sequence in which you jump around. We have zoom in, zoom out capability, which is unheard of in the world of LiDAR. That's equivalent to saying in a mechanical LiDAR, I'm going to take my glass lens or plastic lens and actually deform it every microsecond, change its shape and its property. Impossible. As you know, a lens, let's say a glass lens, based on its thickness, delays light by by the factor that has to do with the refractive index. So there's nothing you can do about changing the property of the lensing assembly. Here we can change the phase value. We can slow down the light with a signal, which would be equivalent to changing at a million points on a lens. It's equivalent to changing the thickness of the glass. So that gives you the ability to do zoom in, zoom out. We can change the frame rate. Each sensor collects 500,000 points per second, one every 2 microseconds. So you can distribute those any way you want across however many frames you want. You can have 1,000 frames per second, each one having 500 points, or you can have 1 frame per second having 500,000 points, and anything in between. We can also enhance the range to the size at the extent of looking forward when you know you have a pre-existing map, that you got to an intersection, and you can actually look further out towards the side at the expense of looking forward, which is okay when you're at a stop sign. You don't have to see more than 50 meters ahead of you when you're at a stop sign, but you would really like to see 150 to 100 meters to the side. All of these 7 capabilities are not supported by any other LiDAR that exists. Any LiDAR we do, it goes through the full battery of tests you have to go through to be qualified to be automotive grade. This is what we did on the mechanical LiDAR. Typical temperature, wide temperature range, vibration, shock, ensuring it's eye safe under all operating conditions. Lifetime, UV exposure, indirect sunlight for the entire lifetime, and so on. That's our first vehicle. You get with the kind of data you see in it. As you're driving around in real time, you see the different layers from each LiDAR. One of our customers, Renault, the sister company of Nissan, basically we had used 4 of our LiDARs. This was the mechanical LiDAR. They put them in 4 corners and they drove around. It turned the vehicle into an autonomous vehicle. They did some highway driving, cone detection driving. They were up and running very quickly because they took not only our hardware but also our software, our perception software, and they were able to collect nice videos. Any snapshot I have of a video, I actually also have the full video on this laptop. So if we have time at the end, if you're interested, I have tons of videos. Let me just keep track of time.
300 meters is the maximum range. What's the minimum range?
Oh, good question. The minimum range for the mechanical LiDAR, which is the one used here, is 1 meter. The minimum range for the solid-state LiDAR is 10 centimeters. So if it's mounted, let's say behind the grill or in a bumper, let's say the way we mounted it in the red SUV, it was behind the grill. basically, if you stand right against it and your legs are touching the bumper, you're more than 10 centimeters away from the sensors. So in terms of time, okay, we have till 5:45. Yeah.
8 in the morning.
Camera will go off. We have some time.
Is that right? Okay. So this is beaming to where?
All around the world.
Is it so streaming live
Yep.
to folks who sign up for this?
The camera will go off, and then you can tell us the real truth.
For the record, I'm telling the real truth. I'm not going to joke about this.
That's no joke around here.
Friday, you can say April Fools, you made everything up.
Two more days to that. It's March 30th today. ADAS, ADAS, as you know, is Advanced Driver Assist System. We can support all the ADAS functions, and you can see them here: lane keeping, park assist, and so on.
Can you do bus detection?
Did you say bus?
Yes, remember Google? He couldn't do
Oh.
a bus from another bus. Can you do bus detection?
Yeah. So, in all fairness to Google, this was
I know.
this was a
It's a
software.
bad joke, sorry.
Yeah, the algorithm was, programmed to assume that if you pull in front of a bus and it's doing less than 20 miles per hour, most likely it's going to slow down. They have not seen how bus drivers drive in the Bay Area.
Talk to a bus driver, clearly.
Yeah. In all the ADAS system that typically had some long range, narrow field of view, short range, wide field of view, radar, and some video cameras might have like this, might have a configuration like this. Everything is color in color can be seen. The hashed area are the blind spots, so you don't have full coverage of the blind spots, and you certainly don't have any visibility for what's coming at you from at an intersection from side streets. With two LiDARs, you get this kind of coverage all around.
Hold on. How are you getting straight behind?
This is a military truck, and we put the LiDARs on the roof.
Oh, okay.
Yeah.
Because the sensors are not, you can't put it behind metal.
Right. It's line of sight. It does not go through metal. Right. So in this case, because with a passenger vehicle, you have to worry a lot about the aesthetics, the aerodynamics. But a big honky truck, you don't care.
So this is like a deuce and a half, 2.5 ton military truck.
Yeah.
Yeah.
Right. So if you stick them on the roof, you can. When you get beyond the shadowing effect, you start to see the back.
Will you be getting into the actual technology of what makes these things work and how?
Yeah. I'm covering the hardware. I showed what the chip looks like and how it works and so on. We'll get into. We still have 25 minutes. Yes. This is the configuration. So very quickly, I mentioned previously what a typical configuration made out of 8 cameras, 6 radar, 12 ultrasonic sensors. If you add a mechanical LiDAR, because you cannot use it to support a safety critical function by itself, and you only add it on top of the existing suite. If it's a solid state LiDAR and you can count on it running reliably, you drop most of the other sensors. You keep 2 radars. So a system that's basically the kind of autopilot system you hear about these days that works on the highway on a sunny day, if there's no shading from a tree on the highway and so on. It costs about $4,000 total. You add a couple of LiDARs. If it's our mechanical LiDAR, you add 2,000. Other mechanical LiDARs, you add 2 times 8, 16, so it costs 20. And the solid state LiDAR plus 2 radar is $1,000.
How many nines does that get you?
How many?
How many nines? You said 10 nines is what you need for autonomous. How much would that system you've got up there for 1,000 give you?
Yeah, our goal is to get to 10 nines. We can. I know it's very challenging. We can get 8 nines, and we have to keep pushing the technology.
How many false positives? How many false positives?
So with 8 nines, that's 1 out of eight nines is
Your false positive, false
one
negative
out
rate
of.
is-
Say it again.
Your false positive, false negative rate is the same?
False positive versus false negative. It really depends on the scenario. It really depends on the scenario.
When you stop when you shouldn't have.
Right. So it could be false positive or false negative. It's it's one out of about one out of about one about in 1 in 10 million situations. So you might miss 1 out of 10 million things that you should have picked up. Yeah. Right.
Is that a sensor restriction, or doesn't that go through an awful lot of software before you?
It does
get
go
to
through a
point?
lot. So this is a system answer here. Yeah, all things considered. So with the software, we're going to keep improving things to get to the closer to the 10 nines. That's going to be all software work because the sensor is what it is, and it's a matter of interpretation and making the artificial intelligence smarter and smarter with deep learning. We have our systems on the garbage trucks of the city of Sunnyvale, basically, and they detect. Sometimes a garbage truck is backing up out of an alley and they don't see well what's coming at them and they get into accidents and so on. I can give you lots of scenarios. We can do object detection, tracking, classification, color coding for each object. You track it and you do scenario analysis, and then you decide on an action plan based on the scenario. Actual trucks of of the city of Sunnyvale. It's with specialty solid waste and recycling. We have, you see, there's one LiDAR here and one LiDAR here. City of San Jose is mapping a corridor for us. So we launched the solid-state LiDAR at CES. This is the Dr. Michael Hafner, who's the Senior VP of Products at Daimler, co-announcing with me on stage at CES the solid-state LiDAR. So this was a big deal for us because this is what we are all about. This is what allows us. This is the entry point into all these applications. Then we make the solution robust and powerful through software, but this is the enabling technology right here. I showed you this vehicle that they gave us. It was running live at the CES. Basically, when you're looking at a person, you see the contour of their bodies. A live image, a video would look nicer because as they move around, you can see how the shape changes. This is the demo done with our LiDAR, a video in front of a rain curtain that was getting heavier sometimes at the NVIDIA booth at CES. And you can read for yourself what Brad Templeton, who's an autonomous vehicle expert, wrote just based on him standing there and watching the demonstration. Basically, when the rain got heavy and the vision failed, the LiDAR kept detecting. We can see through rain. The laser.
Every raindrop?
What's that?
You count every raindrop?
Oh, you can count the raindrops. You can count the raindrops when you're driving through an area that has lots of trees. You can actually count the leaves if you want. The information is there. You just have to ask for it.
How does the sensor work?
We send let's focus on the solid-state sensor because it works differently from the mechanical LiDAR. The mechanical LiDAR is much easier.
Of course, but we were interested in your product. No.
Oh, they're both our products.
Okay.
We also make a mechanical LiDAR.
I'm sorry.
Yeah, that's okay. The mechanical sends one pulse, detects it with an APD, measures the time of flight. It's a time of flight measurement. This is also time of flight, but this is different. This now, here, the detector operates in Geiger mode. So the digital mode, which is basically photon counting mode. That's why the company is called Quanergy. We count quanta of optical energy.
So you are quantum limited.
Well, we are. I'm
Close to quantum limited.
close to
or
quantum
I
limited.
should have asked.
Well, we once you count, once you detect a photon, there's what's called a dead time. We're trying to make that as small as possible. to be able to count the next photon. Uh, we uh, we send the photon pulses that are coded. So that's a pulse train, typically about 10 pulses per shot. Uh, that's coded. So when the signal comes back, we have a match filter that detects the signal out of the noise. When you look at the signal coming back, it looks like all noise. But when you run the match filter, it picks out the signal based on the code.
Pseudo-random.
Pseudo-random. That's exactly right. As GPS does these days. So that's the process. Pulse train, coded, and detection. And we do spatial-temporal correlation to ensure that we are detecting a signal that's a real signal, not a false signal. So we have a SPAD array, single photon avalanche diode array on the receiver side. Behind it, there's an ROIC, readout integrated circuit. Together, they make a receiver. Detector and ROIC make a receiver array. So we we do the detection. We do the single photon counting with the SPAD array. Now the SPAD any SPAD array has an active area and an area that has the circuitry. So you have a fill factor for the active region. We have a good fill factor. Often the fill factor is about 5%. We have 25% fill factor. But still, you don't want a signal to come back at you and hit a dead area that does not have an active zone. So by design, we defocus the signal that comes back so it hits at least a couple of pixels in each dimension. And that's now a spatial correlation. You want multiple adjacent detector pixels to pick up the signal for you to say that I have a real signal. So we have the code, we have the spatial correlation, then we have the temporal correlation. Each one, as opposed to zero in the pulse train, has to give the same information on the range. And when all the pulses in the pulse train give you the same information, you have temporal correlation. The time of flight measured is the same for all of them. When you combine all these three measures, you have rock solid detection, even in a high noise level environment. This is the kind of map we can collect by driving once. This is our office building here in Sunnyvale. Just by driving once around the block, you get this kind of dense point cloud. We can zoom in. This is one of the turns here, and you look at once you collect this point cloud, in a what's called a bag file, it becomes an environment that you can actually do a fly through on your computer, and you can actually fly through just like in a video game and take a still like this from any perspective. So this here we're doing a fly through close to the ground. It shows you a high level of detail. You can see the curvature of the road, the curbs, the lane markings. Now the lane markings, keep in mind I'm only showing you now height. Let me take you to this. You can do color coding based on intensity. In this case, the lane markings, the right turn signal, the stop signs, they really stand out. They really jump out at you. But even when you look at just the height, the resolution is so high that the thickness of the paint is picked up. Just based on height, you can see where the lane markings are.
And that's how you read traffic signs.
And you can read traffic signs that way. You can read traffic signs based on any difference in reflectivity between the lettering and the background. But you can also do it just with video. Just use a $3 cell phone camera. But this is a situation where we said, you can count the leaves on a tree. We've done many applications. We pre-map a course. This is WRC rally race course that we pre-mapped for Hyundai. so they can take very detailed notes before they do the race. It's not allowed to do it during the race, but it's perfectly fine to do it before the race, and then take detailed notes, and now use your handwritten notes for more accurate information. We can do global positioning of point clouds. We can overlay our point clouds on top of satellite imagery, and you can see any changes day to day in the scenery, and you can position yourself and you can detect the changes. Yes, sir.
Isn't this all alternate representations of how your software interprets the data? I still don't understand how the sensor itself works. What are the phenomena that you're using in order to collect this data that you're showing us here?
We are connecting. We have a time of flight sensor. We have an IMU, right, inertial measurement unit, which is accelerometer and
But for instance, how many pixels, what are the dimensions of the sensor? How is it that you're determining the time of flight? What is the emitter? I don't know if these are lasers being put out, but they seem to be blasting the world with energy. What kind of energy does it take?
Okay, so you're referring to when you blast the world with energy, it's called the flash LiDAR approach. We don't do that.
What do you do? I'm sorry.
We have much smaller. We do serial illumination as opposed to parallel illumination. The flash LiDAR does illuminates the entire scene with one big spot. They flash the entire scene. That means the power has to be very high. They use lasers on the order of 100 kilowatt in power, very expensive. To make that eye safe, you go to 1550, cannot detect in silicon anymore. You go to gallium arsenide, 100 times more expensive. That's why those systems cost between $100,000 and $200,000.
So what do you do?
Serial. I have a small spot that hops around 1,000,000 times per second. That's what I do. They flash the entire scene.
So if you're 1,000,000 times per second and your failure rate is 1 out of 10 million, you got a high failure rate.
But that's fine. That's fine because you're collecting so much information that, and you're putting it all together, and it has to make sense. If especially one false signal that does not repeat because it was some random noise, then you know what you're dealing with. And you're gonna eventually, very quickly, you're gonna realize that was a false return. You're running at 30, 50, 100,000 frames per second, and if one of these frames has one dot, that's one point cloud point that's erroneous, you'll figure that out very quickly, within a small fraction of a second.
9 nines is actually a billion, not 10 million.
Say it again?
9 nines is a billion.
Yeah.
10 is 10 million, at least in the United States. I don't know what they do in England.
It's 2.2 times.
Our closest partner for the advanced processor is NVIDIA. We use their Tegra X1 platform for deep learning. It has to be much cheaper for this to go in every vehicle, but for vehicles that collect data to do deep learning and build strengthen the algorithm based on driving around, learning, teaching the algorithm, correcting it in post-processing and so on. That's a very powerful platform. Very powerful platform. I'm gonna be focusing on that topic at GTC next week. So when we collect a point cloud data, the PCL steps basically involve point cloud collection. There is you snap all the frames to the same coordinate system based on the IMU information, so you have a point cloud that's basically clean, where everything is in the same coordinate system. You apply some filtering, Kalman filtering. You do segmentation. Beyond that, you do surface reconstruction based on the segments that you identified after you've done clustering. and then we do object classification. You can do it beyond that, model fitting and more realistic look, give it a more realistic look based on the model fitting. We have data coming in from the LiDAR, from the IMU, and vehicle data on the speed, steering angle, direction of tires. The vehicle has lots of information, and each OEM decides, how much to give you. We have our big wish list of what we would like to have the most robust set of inputs into our perception software. And out of that comes an object list. Now you basically you have positioned yourself. It's you have determined where the ground plane is, where the objects are, what each object is doing, and you put out a constantly refreshed object list. Typically, most OEMs just take that list from you and they take it from there. Yeah, they just tell them 10 to 100 times per second what you're seeing, where everything is. That's all they need. And from frame to frame, you'll track the movement of things. So 5 to 30 hertz PCL point cloud is what automakers ask for. We can go 100, 1,000 hertz, but that's that's a strong capability that's beyond what they ask for. It's just it's a bonus that they get. In terms of the formats, PCL or ROS today, and ADTF in the future. We do have this feedback process where our sensors collect data that gets processed, and our LiDAR software now puts out a map, and that basically it collects the delta between the map you saw and the map that exists, feeds that to the cloud to update the cloud, and the map then that in the cloud now everybody else is feeding their data, and you get assisted with map assist based on everyone's data to refresh your own base map, and that allows us to keep our maps up to date on both the base map and really most importantly the base map, and then what you detect will actually allow you to detect objects on top of the base map. So we have this ability to do real-time 3D mapping, which allows us to communicate road and weather quality conditions, allows us to communicate traffic observations, flow conditions of the traffic, objects, accident, obstacle, debris in real time with centimeter accuracy. We have lane level. We build lane level street maps. The infrastructure is mapped all with centimeter accuracy. We have a full array of location-based services that's included in this capability.
I presume your centimeter accuracy refers to the distance, but there's also an XY. You're trying to scan thousands of pixels or megapixels in order to get a decent image instead of isolated points.
Yeah.
How frequently do you get back to each point, and at what angular dispersion?
At 30 meters, you get 1 centimeter accuracy in all the dimensions. In depth, in X, and in Y. And all of that becomes about 3 centimeters at 100 meters.
And how frequently do you get back and refresh everything with that accuracy?
With every frame, and the frame rate is software controlled by the algorithm based on the scenario. It's 10 to 100 times per second.
So you don't have a higher pulse repetition frequency or anything like that?
No, typically the pulse repetition itself is constant, and how many pulses we have per shot is constant, but how many shots we use to collect each data point, that the algorithm decides on the fly. Any object that's nearby and reflective and so on, 1 shot. if you want to see something very far, you get a weak return from something that's very far, and you want to collect more information and identify its shape and its nature and so on. You can actually send multiple shots and accumulate and fill your the bins of your histogram using what's called TC-SPC, time correlated single photon sensing. Go ahead.
So what's the upper limit that you want a consumer vehicle to drive? 200 kilometers an hour?
Oh, that's
in
fine.
Europe?
That's fine.
Handle that then.
No, absolutely, absolutely. A vehicle moving at 200 kilometers per hour is almost like a car.
Autobahn speed.
Autobahn speed. That's like it's basically standing still compared with the speed of light.
What is the local storage of memory, taking into account temporal filters that can be fairly deep?
Yeah. So are you asking about the platform we use for the storage? Or are you asking about?
Just how much memory is available for the?
There's local buffering inside the sensor, and then we have in the vehicle, but outside the sensor, we have terabyte solid state drive. Were you asking about the type of storage we use? Yeah. So we have both storage on chip, and then we have the post processing. Then we have the data. Post in vehicle processing, we have everything stored on a solid state drive.
That's good for a day or a minute or hour.
It's good for a terabyte is good for 5 days if you drive 8 hours in a day, collecting at the highest resolution. Yep. Oh, okay, I see. So just this is actually my last slide, just to give you an idea. Some public customers I can talk about: the Daimler Group, Mercedes Freightliner, Hyundai, Kia, Renault, Nissan. For OEM, our top tier 1 partner for system on the system level is Delphi. On the component level, which is called the tier 2, it's Sensata Technologies, which is the former sensor division of TI. So the timing is good because that's it. I'm done. We have 7 offices globally, and we are hiring lots of software people. So thank you for your time.
50, yeah.
I've built and sold 3 companies. 2 are telecom companies. 1 is a solar company, and now this is laser sensing. But that's really that's exactly what I worked on for my PhD. And so to avoid too much suspense and people wondering what the product looks like, let's just show it to you right now. That's the solid state LiDAR. You compare it with what we commonly call the KFC bucket on the Google car. This is a smaller, lighter, lower power consumption, completely solid state. Macro level, micro level. So this does not have micro MEMS mirrors that the naked eye does not see. No, nothing moves. Truly solid state based on optical phased array, beam interference. It's an optical version of the phased array radar. And now this, you never see it on a vehicle. So it's not only small, it's also hidden. It's always inside the side view mirrors, in the bumper, behind the grille. And so a car that has this basically looks like it has nothing. And that's the point. That's the kind of car you want to buy. You're not going to buy a car that looks like it has a lab bench on top. It's cool for pilots and yeah. But when you buy a luxury vehicle, you don't want it to have a bunch of instruments on top. So our mission basically is just to do 5 things. That's all we do. We save lives, energy, space, time, and money. And so saving lives is safety, and then the other 4 are efficiency. So we are energy efficient, space, core technology, which is the solid state LiDAR. Having said that, the software behind the solid state LiDAR is where the brains are. And ultimately, we have multiple layers of application and perception, smart perception software, and then scenario analysis, decision making, and so on. All of these layers are laid on top of the basic point cloud that you get out of a 3D LiDAR sensor. We'll talk about all this, and then there's the data you collect, the big shovel that we use to fill the dump truck that the cloud is, and get things processed and fused between different sensors, not just for LiDAR. We'll talk about fusion between LiDAR and video and radar and so on. The company is 3.5 years old, but in terms of introduction, I worked on the core chip that is the core of the solid-state LiDAR 25 years ago. For my PhD, it was sponsored by DARPA. It was the biggest chunk of my PhD at Columbia. Then I went on to get business degrees from, in this order, Harvard, MIT, and Stanford. This is my fourth startup. All my startups are based on, the hardware part of them is always silicon photonics. I like to know my audience. Who here is not CS? Do we have double E's? Do we have MBA folks? Double E, please, I really want, okay, great. So like a handful of double E's? Okay, right, so we won't talk only about the software, we'll talk about the hardware as well. We're gonna cover everything anyway, but I won't skip the hardware part. Let's see, any business
This is
folks?
not fresh.
Even if your background is double E or CS. Okay, great. My business cards are here, you can grab them afterwards. I have some props, yeah, we'll get to them. I have a lot more material than we can cover in an hour. Just I'm always ready for any questions. I can jump around. Do you all know what Quanergy does? We do. I mean, it's really hard to not know what Quanergy does these days. We're almost in the news every day. We've been getting almost every award. Top 10 startup, top 10 this, and top 2 this, and which is great. But that comes with lots of hard work and resulting business activity, which is also great. But that comes with very little sleep, which is okay. So we make LiDAR. We are famous for our efficient, time efficient, and cost efficient, our solutions. My background in the industry, I'm going to just flash this. I'm not going to spend too much time on this. Just so you see the companies I worked with and sold, and then I stay with the parent company for many years, actually, typically, which is not common for entrepreneurs. And then we did some acquisitions over time. Long story short, I started after my PhD at Allied Signal in Morristown, New Jersey. We became Honeywell after we acquired Honeywell. Started 3 companies, sold them, sold 1 company to Corning, 1 to DuPont, 1 to SK Energy in Korea. Became the CTO of Sun Edison, and then now Quanergy. What we are about disruption through innovation and through business model innovation, technical and business model innovation. We disrupt the transportation space as well as security, industrial automation, mapping, digital navigation, as well as location-based services. In mapping, we are mapping the world, making a unit like this, the solid-state LiDAR, making it available for a couple $100, meaning our cost, you can guess, is about half of that. Allows it to go in every vehicle now. It's no longer the $80,000 unit that you see on a typical Google car. We love Google, by the way, not trying to say anything bad about Google. It's just, I mean, they use it to develop software, right? So whatever works to develop software, that's fine. So, but in that case, when it's a mechanical LiDAR and you're using it for development, to develop software, if it breaks, okay, you go back to the shop, you replace it. But when you're using it to actually enable an autonomous vehicle and you're taking a nap, it's not as cool when it breaks. It has to be solid state. And that's not just our opinion because we have this. We have this because that's what the customer said. Location-based services. Ultimately, you can imagine a smart IoT, Internet of Things, where each thing doesn't just tell you where it is, it shows you everything that's going on around it. And that's a very smart IoT. So business model, basically, yes, we do have core hardware technology. We have a lot more software than hardware, multiple layers that I described, and ultimately we will get into data services. And that's our ecosystem. We have the core hardware, the data processing on board that controls the systems that control the vehicle. And we build maps using that data. We have we communicate in real time using a cellular connection. Observations. An observation can be any object around you, a pedestrian vehicle, debris, pothole, etc. It can be a traffic condition, a weather condition, accident, so on. All of that gets communicated immediately via a cellular connection.